in that case, you can use the CDF principle, that you find the CDF of the new random variable, and once you get the CDF, you differentiate it, you get the PDF.
So we can't see your screen.
You are not able to hear?
No, so the screen is not visible.
Yeah, screen. I was just giving an intro. So anyway, so I was just trying to explain you that what I did yesterday, and anyway, let me share. So. So I was just summarizing that what I did yesterday, that you have a random variable X, and then you have to find the PDF or PMF of a new random variable Y is equal to GX. And I took two examples for the discrete case and few examples for the continuous case. And ultimately, there is a result which can be directly used, which is given in the form of the theorem. But this result is valid only when the function is either increasing or decreasing. So you can directly use this final result, that fyy is equal to fx g inverse y dx, absolute value of dx over dy. And I gave you the proof of this result. Now, the first example which I discussed using CDF, I used this same example to demonstrate that how the formulas which we have derived can be used. So having done that, I gave you the general result, because what happens when function changes its behavior in a different range, say maybe either increasing or decreasing. So say for example, y is equal to x square or y is equal to mod x. So one can directly derive using the CDF, but there is a general theory. Of course, it is an advanced topic, but I still stated the result, that you have to break this range, the domain for which the density function is defined, into several domains, which is represented by chi1, chi2, chi_m, and in each case the function each y equal to gx defines the one-to-one transformation, and once we have done that, for each case we can find the inverse x equal to g inverse y. So the combined result will be the summation of summation over I is equal to 1 to n, and the same formula you apply in the respective domain, and combined it, you will get the result. So same example you can solve using this formula, that you have two regions. One is from minus infinity to 0, one is 0 to infinity. So we have the functions. So in one case it is decreasing, another is increasing. So in that case, the final result you can write here in this form. So as I told you, it is an advanced topic. You may not find the books which we have prescribed at your level, but still you can work out the problem wherever such type of situation arises. So next thing is that sometimes, hello.
Sir, I have one question, sir.
हाँ,
Sir, for
बोलो.
equality case, what we will consider, decreasing function or increasing function?
For equality case,
Like minus infinity to 0 and 0 to infinity, what will consider for 0? Or which function will?
for 0 actually, say minus infinity to 0, it is basically a continuous function. So either of the side you can include. The first here we did the minus. If you look
Sir,
at
for
the first,
decreasing, you didn't included the 0. You only Yeah, here it is.
I did not include, but you can include 0. Okay.
Okay, sir.
Okay. You can include 0. I did not write, but you can include 0. So next thing is that sometimes we may need to find, say, x1, x2, xn are an independent random variable, and their respective density function or distribution function is given. So our job is to find out that what will be the distribution of minimum and distribution of the maximum. So there are x1, x2, xn and random variable. What will the minimum, we define minimum of that by minimum x1, x2, xn, and this we represent by y1, and similarly maximum of x1, x2, xn we define by yn. So why I am discussing this result, again, this is an advanced topic, but most of the times we use such type of result, and it is not very difficult to get the distribution of y1 and yn. Basically, there is an area which is known as the order statistics. We take we have n random variable and we put them in the order. Then we have to find the distribution of the certain order statistics. If minimum, this is the y1 is the first, which is the minimum. Yn is the maximum, and in between any order we can find out. So we are not discussing that much into detail, but minimum and maximum is easier to find out, and I'm just trying to show you that what will be the final digit. So y1, as I told you, this is the minimum of n random variable. We need to find out what is the CDF. Okay, and once we have the CDF, we can get the PDF. So as I told you, you write down the definition of the CDF. So probability, it will be y1 less than y, and y1 we have defined minimum of x1, x2, xn. So we can write into complementary form, y1 is greater than y. So in place of y1, we write minimum of x1, x2, xn is greater than y. So, and remember that these are the independent random variables. Okay. So if the minimum is greater than y, certain number, then all other, what this implies? If minimum is greater than y, means x1 is greater than y, x2 is greater than y, xn is greater than y. Means minimum of whatever that you take the minimum, if that number is greater than y, then all other numbers will also be greater than y. So that using that concept, we have written x1 will be greater than y, x2 will be also greater than y, xn will be also greater than y. And since they are independent, we can write probability x1 greater than y, x2 greater than y, xn greater than y. So so actually some mistake is there. So you come to this page. So so this I can write product I is equal to 1 to n xi greater than y. You come to this page. Okay. So one probability I product I is equal to 1 to n xi greater than y. So this is again I can write in form the complementary form. So it is equal to 1 minus it is equal to 1 minus this expression. I have written 1 minus, so this into this form. Okay. So this is nothing but the CDF of xi. So 1 minus product I is equal to 1 to n, 1 minus fxi y. This is the CDF of xi. So I just substitute. Now if all have the same distribution, all x1, x2, xn have the same distribution. Say for example, they follow the exponential distribution or they follow the normal distribution. So in that case, xi
Sir, you are muted.
Sir, you are muted.
So up to this it is fine. Up to this it is okay.
Yes.
So now the particular case of this, that all the xi's have the same distribution. So we represent it by f dot. So fxi is equal to fx for all I. Okay, here it is I. Okay, so this is I, not. Okay, so fxi is equal to fx for all I, and when we substitute, so it becomes 1 I is equal to 1 to n, 1 minus fx, and it can be written in the powers. Okay, so this is the final result when they have a identical distribution. Now if we want to take the derivative, means if I want to find the PDF, so I have taken the derivative with respect to y. So this is 0, this is n times of this bracket, which is power n minus 1, and the derivative of inside. So derivative of inside will be derivative of fx. So the derivative of fx means the density x represent the CDF of random variable x. So it becomes the density function of x with dummy variable y. So if you write this, it will be n1 minus fxy power n minus 1 small fxy. So this is the standard result, that CDF of density function of the minimum of this n random variable if they have an identical distribution. If they are not identical distribution, then we have this result, earlier result which we have derived. So for example, if all the xi's follow the exponential distribution, okay, with same parameter lambda, then the CDF is 1 minus e to the power minus lambda x, and density function of x is lambda e to the power minus lambda x. So simply if we substitute here in this, so the red mass, so then you will get n times all I have substituted with you have to take care of y. So it is 1 minus e to the power minus lambda y, then density function of x in terms of y has been written. So if you simplify this, you will get this result. So this is a very good result in the sense that if x1, x2, xn are n independent random variable, and all they follow the exponential distribution with parameter lambda, then the distribution of the minimum of n random variable will follow the exponential distribution with parameter n lambda. Because if you look at this, here it is exponential with parameter n lambda. Okay, so this is a very good result, and most of the application we can use this directly, that whenever we have to deal with the minimum of x1, x2, xn, then the distribution will be exponential. So coming back to the previous one, yeah, so here now we come back. So now if we, so here you move to page 11. Okay, now we are coming back to again. Suppose we have to find the maximum. So same way we write the CDF of yn, which is yn less than y. Yn is nothing but maximum of x1, x2, xn is less than y. If the maximum of certain quantity is less than y, then all other quantity will also be less than y. So in that case, x1 will be less than y, x2 will be less than y, xn will be less than y. Since they are independent, so we can just write x1 probability of x1 less than y, x2 less than y, xn less than y. And when we put in the product form, it is I is equal to 1 to n, xi less than y. So this is nothing, the CDF of xi. So we can write into the product form, and as I told you, if all of them have a identical distribution, then we can write fx and power n, and if you differentiate this, you will get the PDF of yn. Yn is maximum of x1, x2, xn is n times fx y power n minus 1 into density function of x. With this variable you have to take care of. So same way that of course here we cannot simplify in a more compact form. So if x follows the exponential, then distribution of the maximum can be written into this. So all these distributions, all these functions, basically this is also minimum and maximum of n random variable are known as the function of n random variable. So they are used frequently in reliability theory and various other places. So I thought that let me give you an idea that what do we mean by the minimum and maximum. So because so far we have not discussed the joint distribution. Okay. So all these are the parts of the joint distribution of n random variable. But still, since they are independent, results become much simpler. So having done that, now the lastly, what we are going to discuss, that given a random variable x, we know how to find out the density function or distribution function of the new random variable y is equal to gx. And we have seen the result that if g is monotonic function, then how to get that result. So in general, we have proved a theorem. Now this g I am taking as CDF, because we have seen the CDF. What is that CDF function? F dot, capital F dot, and it has certain properties that it is a non-decreasing function, it is right continuous. So CDF is also one of the function basically. Okay, so in place of G, if I take capital F, and the capital F, the property is known that it is a non-decreasing function. So what will be the distribution of that y is equal to capital F x. Here x is also capital. In place of G, we are going to write capital F. So the now, as I have written, now let us choose G dot as F dot. Okay, and F dot is nothing but CDF function. So our problem is to find the CDF of the random variable y is equal to fx. Okay, we have to find this. Okay, in place of G, I have chosen a particular function, and the particular function is our CDF. So I can write in place of G, I can write capital F. So how to get this? Now here, the symbols may cause you the confusion. So in order, basically what we need to find out, f y y. Okay, CDF of y, but since f, this capital F you are using here as a function. Okay, this f. So I have used a new notation HYY. Okay, this is HYY. What this represents? This is nothing but the CDF alpha. instead of using the standard notation fyy, I am using the CDF of y, which is denoted by hy. Okay, just to avoid any confusion with f. Okay, so by definition, hy is y less than y. Okay, since y equal to fx, we have defined. So I will simply substitute y in place of y, capital Fx. Okay, capital Fx less than y. Since f is a non-decreasing function, it's a monotone function, as we know. So x, I can write f inverse y. Okay. Now here again, since the CDF of x is known, CDF of x, we have stated from the beginning that if x has a density function fx, and here you can write that its CDF is fx. Okay. This is not. So I will substitute this at f x of f inverse y. Okay. Basically, the meaning of this, here if you see what I am writing, this is the CDF of x. So fx, f inverse y, also f is the CDF of x, so fx f inverse y. So instead of this, we have simply written f inverse y. So if you are if you have little confusion, then you can assume that alpha equal to f inverse y. So x is less than alpha. You write fx alpha and then fx inverse y. So it is a re-explanation of the same thing by. So this is the crucial step we have to understand from here to here. Is that fine? So now this gives you simply y. Okay. So the CDF of y is y, and y varies from 0 to 1. Okay. Now, so if you remember, we have got the result. This is the CDF of y, which is where y is equal to fx. Okay, this is what we started. That we need to find out what is this CDF of y, that we have got y. Now, what is this? This, if you remember, is a uniform distribution. In uniform distribution, x follows alpha and beta. So its CDF is there, 0, x less than alpha, alpha beta. This we have earlier derived. So if I take alpha 0, beta 1, then you get this form. Okay. So this is identical to this. Because here, because all other places between 0 to 1, it is here it is y. Okay, so special case of this, when alpha is 0, beta is 1, it is known as the uniform distribution with 0, 1, and its CDF is fx equal to x. So the distribution of y, so what is the final result? Final result, what we have derived, that if x is the random variable whose CDF is capital F, then the distribution of y is equal to fx, okay, has a uniform distribution over 0, 1. So this is the final result, that y is equal to fx. Okay, y is equal to fx follows uniform distribution. Okay, uniform distribution means 0 to 1. So this particular transformation is known as the probability integral transform, and it is basically used to in simulation, that you have a you can generate the random number from uniform distribution, and from there you can get the distribution of and say for exponential, normal, etc. So again, these are the advanced topic, but this transformation, as I told you, is known as the probability integral transform, is very useful, and that's why I thought that should be given. So is it fine? The crux of the issue is here that instead of G, you consider capital F. That's all. And then you try to find out the distribution. New random variable y is equal to F.
Sir, the range of y should be 0 less than or equal to y less than or equal to 1, right?
Y will be between 0 and 1.
Including 0 and 1. Or excluding.
ठीक है that y equal to 0 to 1, because your CDF is in this form. So ultimately it is a continuous function. So it does not matter. Okay. So uniform distribution both in it is a continuous random variable. So either you include or exclude, it will not make much difference.
Thank you.
Okay. So this covers your covers the topic of the function of random variable. So almost we have covered the univariate case. Univariate case means we started with a single random variable and we discuss some of the standard discrete distribution, some of the standard continuous distributions. Then we discuss the transformation, means how to find out the distribution of a transformed random variable if the distribution of the original random variable is given. So almost we are done with the univariate case. So now we shall move to the next topic, which is known as joint distribution. Joint distribution means basically you are going to deal with more than one random variable. So the theory is quite vast, but in this particular course, our concentration mostly will be on the distribution of two random variables, means x1, xy, or x1, x2, something like that. But theory is there that one can study the joint distribution of n random variable and many other things. So the idea behind is that we will be studying the joint distribution of two random variable, and ultimately we will discuss the bivariate normal distribution. Because you have done the normal distribution, now we shall be discussing the distribution of two random variables, and they follow jointly normal. An extension of this is multivariate normal. So we are not going to discuss that much. So now I'm switching over to the next topic. So So this as so to motivate you, what do we mean by joint distribution of the two random variable or three random variable? So as I told you that our concentration will be on two random variable. So let us consider a problem that we have an arm which consists of 3 red ball, 4 white ball, and 5 black ball. And from these 3 balls are drawn without replacement. And when you get 3 balls, you would like to know how many red balls are there and how many white balls are there. Okay. So we define two random variables. One is x, because in 3 the number of red and number of white balls will vary. So simply these two are random variables. So for the sake of simplicity, we denote X as a number of red balls, Y as a number of white balls. Okay. So what is our objective? I may be interested in knowing what is X equal to 1, Y equal to. X equal to 1, Y equal to 2 indicates what is the probability of having one white ball and two, sorry, what is the probability of getting one red ball and two white. X is for red, Y is. So in general, I can find out the distribution that we usually write in the tabular form. So we make a square, rectangle or square depending upon the numbers. These numbers 0, 1, 2, 3 need not be the same. So as you will see in different examples. So here, as you can see, what will be the range of X and what will be the range of Y? X is the number of red balls, Y is also the number of white balls. So in a sample of size 3, the number of red balls could be 0, 1, 2, 3. So we have written 0, 1, 2, 3. Here in the top row, so we can write the random variable Y, and Y is the number of white balls. So in a sample of size 3, the number of white balls could be 0, 1, 2, 3. So we have written this. So now we have to find out what is the probability X equal to 0, Y equal to 0, X equal to 0, Y equal to 1, X0, Y2, etc. So to start with this, I have done X0, Y0. What this indicates? X0, Y0 means when you have drawn a sample of size 3, the number of red ball and number of white ball both are 0. It means what is the probability of this? So when both the color are absent, certainly all the three balls would have come from the black. So this probability will be 5C3 by 12C3, because your total number of balls are 12. So from 12C3 and here basically 3C0, 4C0 and 5C3. So if you simplify this, you will get 10 by 220. Similarly, if I am interested X0, Y1, X0, Y1, X represents the number of red balls and Y represents the number of white balls. So no red ball, one white ball. It means there must have come two black balls, because total number of balls you have drawn is 3. So here in this case, X0, Y1, so 4C1 and two black ball must have come. So 5C2 divided by 12C3, 40 by 220. So like this, I can calculate all these combinations. Okay. So having, say for example, X0, Y0, we got 10 by 220. So 10 by 220, I will write here. Similarly, X0, Y1, X0, Y1 we have calculated. So it is coming 40 by 220. I have written 40 by 220. Similarly, X0, Y2, 30 by 220. Then calculate X0, Y3, 4 by 20. Similarly, 10, 11, 12. Now 13. 13 indicates one red ball and 3 white balls. 13 means 1 red ball and 3 white balls, which is not possible, because total number of balls are drawn are only 3. So here this probability will be 0. Similarly, 2, 2 will be 0, 2, 3 will be 0, 3, 1, 3, 2, 3, 3 will be 0. All other places you can calculate the probability the way we have done for 0, 0, 0, 1, etc. So having filled this table, okay, 0, 0, 0, 1, 0, 2, 0, 3, 1, 0, 1, 1, 1, 2, 1, 3. Now if I want to find out what is the distribution of X, means instead of finding the joint probability of the number of red and number of white balls, if I am interested in only finding the distribution of X, means probability mass function of X and probability mass function of Y, so this table will give you that result. What we do, because X is the number of red ball in a sample up size 3 which has been drawn. So number of red balls could be 0, 1, 2, 3 only. So what here 0, 1, 2, 3 you write. Okay. Now if I sum the row sum means you are summing over other values of Y. Okay. So it is 84 by 220. Similarly, this row sum is 108 by 220. This row sum is 27 by 220. This row sum is 1 by 220. And similarly, I can sum the column also. So when I sum the column, it is 56 by 220. It is 112 by 220. It is 48 by 220, 4 by 220. So this column, the last one, the column where the sum has been obtained, this represents the probability mass function of the random variable X, because X equal to 0, 84 by 220. So to find X equal to 0, you have sum over all possible values of Y, because 0, if X is 0, then Y could be 0, X equal to 0, Y could be 1, X equal to 0, Y equal to 2 and 3. So similarly here X1, so I have summed over all possible values of Y. So this last column where the sum has been written gives you the probability mass function of X, and similarly the last row, that if I sum the columns, okay, here we have summed the row, now we have summed the column. This gives you the probability mass function of Y. So Y equal to 0 is 56 by 220. Y equal to 1, 112 by 220. Y equal to 2, 48 by 220. Y equal to 3, 4 by 220. And the usually we, because this is the probability mass function of X, sum should be 1. This should be probability mass function of Y, it should be 1. And in fact, here the probability mass function, the joint probability mass function, if you sum over all possible values of X and Y, then sum will be 1. Means basically, if you sum this all the elements which have been put in this rectangle, then sum will be 1. So this basically sometimes provide you a check whether your calculations are correct. Say if this is not coming 1, then something is wrong. So here ultimately we can write the probability mass function of X, probability mass function of Y. So in general, mathematically, we write probability X equal to X, Y equal to Y as P X Y, the capital X Y, as I told you, we put the subscript, and these are the values X and Y. So in probability theory, the subscript plays an important role in the sense that it identifies the random variable under consideration. Okay. So, and it also represents the order, means X takes value X, Y takes value Y. So this function is known as joint probability mass function of the random variable X and Y. Okay. Or sometimes we also call joint distribution of the random variable X and Y. As I told, as we have seen from the table, that if I sum this joint probability over all possible values of Y, we get probability mass function of X. And similarly, if I sum over all possible values of X, then we get probability mass function of Y. So these are known as marginal distribution of X, marginal distribution of Y. So this is the joint distribution, and these are the marginal distribution of the respective random variable. Sometimes another sort of notations are used, that x takes value x1, x2, x3, y takes value y1, y2, y3, y4. So the elements can be written in this form: p11, p12, the way we write the matrices basically, p13, p14, like that. Now here the summation, when you are summing over all the possible values of y, that basically you are summing over the second subscript. So we write p1 dot. So dot represent means basically you are summing over second value. Similarly, here also p2 dot, p3 dot, and similarly if you are summing over the first subscript, then p dot 1, p dot 2, p dot 3, p dot 4, and if you sum all of them for both the subscript, it gives you p dot dot. So here basically also, as I told you, that if we sum this for the first subscripts, p dot dot, and this is another p dot dot. So usually in some books you may find this notation also, that pij, small pij, is probability x equal to xi, y equal to yj, or simply they write probability x equal to y, y equal to j. And pi dot is means summation over the second subscript, and this indicates the summation over the first subscript. Why it has been done in the sense that here we are dealing with the two random variable. If the number of random variable increases, say x, y, z, so in that case these notations helps you to write the things. Of course, in the case of three random variable, we cannot represent it in the tabular form, but still these notations helps us in deriving various results. So in general, if we have say four random variable x, y, z, w, then joint probability of x equal to y, y equal to j, z equal to k, w equal to l is written as p I j k l, and summation over all possible value of I j k l is written as p dot dot dot. So dot 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 means you are summing over y, summing over j, k, l. If you have to find probability x equal to y, then it is pi dot dot, means you sum over other values of random variables, that is j, k, l, then you get the marginal of x. So having defined the joint distribution of the, is it fine up to this?
Yes, sir.
So having done the joint distribution, we can find the conditional distribution. So again, a set of notations are introduced. So given the joint distribution, how to find out the conditional distribution? Conditional distribution means x equal to x1 given y equal to y. Means the second variable takes the specific value y2, then what is the probability that x will take value x1? So in order to calculate this, we simply apply the conditional rule. So this gives you probability x equal to x1, y equal to y2 divided by probability y equal to y. Okay, joint probability divided by the this one. So this, in terms of the notation, we can write p12. Okay, and this is, you require the marginal distribution of y. Okay, so this we have written p dot 2. Okay, means, so in general, x equal to xi, y equal to yj, we write pij divided by p dot j. Or simply you can remember x equal to xi, y equal to yj, and then the marginal distribution of yj. Y. So this is the conditional definition. Now, when do we call the two random variables are independent? Okay. So x and y, because now the random variables which we are discussing are two. Instead of univariate case, everything we were dealing with for one random variable. Now, since you have two random variable, they may be independent or they may not be independent. If they are not independent, is somehow they are dependent on each other. How much the dependencies there are, how much they are related. So these questions will be answered. How to measure their relationship between these two random variables. So let us first discuss the condition for the independence. So if x and y are independent random variable, so we write the joint probability as written as product of their marginals. So it is same result as you have seen, the probability of AB equal to probability of A into probability of. So from here also we can derive that uh, if uh, y is independent of xi, then conditional distribution of probability x equal to xi given y equal to yj will be equal to probability x equal to xi. So this will be equal to probability x equal to xi. So cross multiply, you will get this result. So
Sir,
the important thing,
this is for every IJ, na?
This is for all. That's what I am going to tell you. If for any particular ij, even one condition does not hold true, then we cannot say the random variable x and y are independent. And I will show you by means of a example also. So here, this is important. For all I and j, it should be true. So here, one example I am showing that how to check that x and y are independent. So here you see the x takes value 2 and 5, y takes value 0, 2, 5. So these numbers are given, and then you find the marginals of x and marginal of y. Now, if I have to check that whether x and y are independent or not, okay. So what I have to do? P20. P20 means probability x equal to 2, y equal to 0. Must be equal to probability x equal to 2, y equal to 0. So this is the joint probability, this is the margin. So in this case, P20 is, as you can see, 0.06. P2 we have obtained 0.3. P0 is 0.2. So it is 0.06. So basically what you do here, this this cross multiplication you have to do. Say 0.20, 0.3. So this will give you 0.06. Similarly, 0.5, 0.7. This, if you see, you will get 0.35. So in all the cases, as you can see, 0.2 into 3, 0.15, 0.2 into so all the cases, 0.3 into 0.3 is 0.09. So in this case, the product rule is satisfied in all the cases. So all the joint probabilities can be written as product of their margin. So instead of writing this way, you can also cross verify this way. Okay. So in this case, x and y are independent. If they are not independent, I will come another example to show you. So if any one of the conditions is violated, then we can say that we cannot say that x and y are independent. So if they are not independent, they will be dependent, and if they are dependent, then we measure their correlation. So all these concepts will be discussed in the next class. So before that, we will describe few more results, that what will be the expectation of x plus y, expected value of x, y, all these results are used. So knowing the joint probability mass function, all these quantity we can easily output. So in the next class we shall discuss. I have uploaded this document. Okay, is it fine? Any question you have? We will stop at this point.